Introduction to G-Cloud MIG commands. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with a focus on networking. Today's presentation is a deep technical dive into G-Cloud commands for managed instance group auto-scaling. If you've ever been confused by the various parameters, flags, and options available in these commands, this presentation will clarify everything. We'll examine every parameter available in the G-Cloud Compute Instance Group's managed commands related to auto-scaling. I'll explain what each parameter does, when to use it, what values are valid, and how different parameters interact with each other. This is not just a reference guide. I'll provide real-world context for each parameter, explain the implications of different values, and share insights on optimal configurations based on common use cases. By the end of this presentation, you'll have complete mastery of G-Cloud auto-scaling commands. You'll understand not just the how but also the why behind each parameter, enabling you to configure auto-scaling precisely for your specific needs. Let's start by understanding the overall structure of G-Cloud commands for MIG auto-scaling. There are three main commands you'll work with, each serving a different purpose. The set autoscaling command creates a new autoscaler or completely replaces an existing one. This is your primary command when initially configuring autoscaling. It requires you to specify all the essential parameters because it's creating the autoscaler from scratch. The update autoscaling command modifies an existing autoscaler without replacing it. This is useful for tweaking parameters or adding schedules without disrupting the current configuration. You only specify the parameters you want to change. The stop autoscaling command deletes the autoscaler entirely. Unlike setting the mode to OFF, this completely removes the autoscaler configuration. You'd need to use set autoscaling again to re-enable autoscaling. All these commands follow the pattern G-Cloud Compute Instance Groups Managed, followed by the command and the instance group name. For zonal MIGs, you add zone equals zone, and for regional MIGs, you use region equals region. This scope specification is mandatory, as the command needs to know which MIG you're configuring. Understanding when to use each command is crucial. Use set autoscaling for initial setup or major reconfigurations. Use update autoscaling for incremental changes. Use stop autoscaling when you want to permanently disable autoscaling and manage instances manually. The core scaling parameters define the fundamental behavior of your autoscaler. These are the essential settings that every autoscaler needs, regardless of the scaling metric you choose. The max num replicas parameter sets the absolute ceiling for your instance group. This is your cost control mechanism. No matter how high the load gets, the autoscaler will never exceed this number. Set this based on your budget constraints and the maximum load you realistically expect. Common values range from 10 for small applications to 1000 or more for large-scale services. The min num replicas parameter sets the floor, the minimum number of instances that will always run. This ensures baseline capacity and prevents cold starts. Even with zero load, this many instances remain running. Set this based on your minimum availability requirements and acceptable cold start tolerance. This typically ranges from 1 to 3 for development, to 10 or more for production services. It's important to understand that these aren't just suggestions, they are hard limits. The autoscaler will never violate these boundaries, even if metrics indicate it should. If your max is 50 and you're at 50 instances with 100% CPU, the autoscaler cannot add more instances, regardless of the load. The relationship between the minimum and maximum also matters. A narrow range, for example, a minimum of 8 and a maximum of 10, provides predictable costs but limited elasticity. A wide range, such as a minimum of 2 and a maximum of 100, offers great elasticity but less predictable costs. Most production services use a ratio of 1 to 5, to 1 to 10, between the minimum and maximum. These parameters apply regardless of your scaling metric. Whether you're using CPU, HTTP, or custom metrics, These limits always constrain the autoscaler's decisions. CPU utilization parameters. CPU-based scaling is the most common starting point, and its parameters are straightforward but require careful tuning for optimal results. The target CPU utilization parameter is a decimal between 0 and 1, representing your target CPU percentage. For example, 0.60 means 60% CPU utilization. This is not a trigger threshold. It's a target the autoscaler continuously works to maintain. If you set 0.60 and your instances are at 80%, the autoscaler calculates how many instances are needed to bring the average down to 60%. Common values range from 0.50 to 0.80. Lower values, like 0.50, provide more headroom for traffic spikes but cost more due to idle capacity. Higher values, like 0.80, are more cost-efficient but leave less room for sudden load increases. For web applications, a range of 0.60 to 0.70 is often optimal. For batch processing, a range from 0.80 to 0.90 might be acceptable. The CPU utilization is calculated as an average across all instances in the group. This means some instances might be at 90% while others are at 30%, but if the average is 60%, the autoscaler considers the target met. This averaging can sometimes mask hotspots if your load balancer isn't distributing traffic evenly. The autoscaler uses a predictive algorithm, not just the current CPU. It looks at trends over the past few minutes to anticipate whether CPU is rising or falling. This helps prevent overshooting the target but can sometimes make the autoscaler seem slow to respond to sudden changes. One critical consideration is that CPU metrics have a delay. It takes 60 to 90 seconds for a new instance's CPU metrics to appear in monitoring. During this time, the autoscaler might make decisions based on incomplete data. This is why proper cool-down periods are essential with CPU scaling. When your MIG is behind a load balancer, you can scale based on load balancing metrics, which often provide more responsive scaling than CPU for web applications. The scale based on load balancing flag enables this mode. This flag tells the autoscaler to use utilization metrics from the load balancer instead of CPU. This only works if your MIG is configured as a backend service for a Google Cloud load balancer. The target load balancing utilization parameter sets your target utilization as a decimal. But what does this utilization mean? It's calculated based on your backend service configuration. If you've set a max rate per instance of 1000 RPS in your backend service, and this parameter is 0.80, the autoscaler maintains approximately 800 RPS per instance. This utilization can be based on different capacity settings in your backend service. If you use the max rate per instance parameter, utilization is based on requests per second. If you use the max utilization parameter in the backend service, it's based on that target. The autoscaler respects whichever capacity constraint you've configured. One major advantage is responsiveness. Load balancer metrics update almost instantly when traffic changes, unlike CPU which lags. The autoscaler can start adding instances as soon as traffic increases, before CPU or memory usage climbs. This makes it ideal for applications with sudden traffic spikes. The interaction with backend service configuration is crucial. The capacity scaler on your backend service acts as a multiplier. If set to 0.5, each instance is treated as having half its configured capacity. This is useful for canary deployments or when instances have varying performance. Remember that this parameter completely replaces CPU scaling. You can't use both simultaneously on the same autoscaler. Choose based on what better represents your actual load. Custom metrics parameters. Custom metrics offer the most flexibility but also the most complexity. These parameters let you scale based on any metric available in cloud monitoring. The custom metric utilization parameter has a specific format. Metric equals metric name, utilization target equals target, and utilization target type equals type. Let's break this down. The metric field is the full cloud monitoring metric name, like custom.googleapi.com/q/dev or pubsub.googleapi.com/subscription/num undelivered messages. The utilization target is your target value for this metric. The interpretation depends on the utilization target type. If the type is per instance, this target is per instance. For example, a target of 100 with per instance means each instance should handle 100 units of whatever you're measuring. The utilization target type can be per instance or gauge. Per instance is for metrics that scale linearly with instances, like requests processed per instance. Gauge is for metrics that represent a total across the group, like total queue depth. With gauge, the autoscaler adds instances to handle the total value, not a per instance value. You can specify multiple custom metrics by repeating the parameter. For example, you might scale based on both queue depth and processing latency. The autoscaler scales up when any metric exceeds its target but only scales down when all metrics are below their targets. This provides a safety net for complex applications. The Stackdriver metric filter parameter, which is a legacy name but still supported, lets you add filters to your metrics. This is useful for metrics with multiple time series. For example, you might filter by response code to scale based only on successful requests. Custom metrics must update at least every 5 minutes for the autoscaler to use them effectively. Stale metrics cause the autoscaler to stop making decisions, potentially leaving you stuck at the current instance count. Timing parameters control how quickly and smoothly your autoscaler responds to changes. Getting these right is crucial for stability and performance. The cooldown period parameter, specified in seconds, is perhaps the most important timing control. After any scaling event, the autoscaler waits this long before making another scaling decision. The default is 60 seconds, but this often needs adjustment. Applications with slow startup times might need 180 to 300 seconds to prevent new instances from being added before previous ones are fully operational. Why is this so important? Without adequate cooldown, you can get flapping, a rapid scaling up and down. The autoscaler adds instances, but they take time to start. During this period, metrics can look worse, so the autoscaler adds even more instances. Then, when all the instances are finally running, the metrics drop, which triggers a scale down. This wastes resources and impacts stability. The initial delay parameter sets how long to wait before a new instance's metrics are included in autoscaling calculations. During this warm-up period, the instance is running and handling traffic, but its CPU or other metrics are not affecting scaling decisions. This prevents artificially low metrics from starting instances from triggering unnecessary scale-up. For production services, I recommend setting initial delay to match your application's typical startup time plus 30 seconds. If your app takes 2 minutes to fully warm up, set this to 150 seconds. This ensures the autoscaler makes decisions based on steady-state performance, not startup behavior. These timing parameters interact. Your cooldown period should generally be at least as long as your initial delay. Otherwise, the autoscaler might make decisions based on incomplete data from recently added instances. A common pattern is cooldown equals initial delay plus 60 seconds. Scale down control parameters. Scale down controls prevent overly aggressive instance removal, which can impact service stability and user experience. These parameters give you fine-grained control over how instances are removed. The scale-down control max scaled-down replicas parameter limits how many instances can be removed in a single scaled-down event. If set to 10, even if the autoscaler calculates that 50 instances should be removed, it will only remove 10. This prevents sudden capacity drops that could overwhelm remaining instances. This parameter works within the time window specified by the scale-down control time window parameter, given in seconds. Together, they define a rate limit for scale down. For example, max scaled down replicas equals 5 with a time window of 600 means at most 5 instances are removed every 10 minutes. But there's more complexity. The autoscaler can perform multiple scale-down events within the time window, as long as the total doesn't exceed the max. With our example, it might remove 2 instances, wait 3 minutes, then remove 3 more, staying within the 5 per 10 minutes limit. The scale-in-control max scaled-in replicas and scale-in-control time window parameters are newer aliases for the same functionality. Scale-in is technically more correct, as removing instances scales in while adding them scales out, but both sets of parameters work identically. These controls are crucial for stateful applications or those with long graceful shutdown periods. If instances take 2 minutes to gracefully terminate, rapid scale down could leave you with many instances draining simultaneously, unable to handle new requests. A good starting point is setting max scaled down replicas equal to 10 to 20% of your typical instance count, with a time window of 300 to 600 seconds. Adjust based on your application's ability to handle load redistribution. Schedule parameters allow you to proactively scale based on time, rather than reactively scaling based on metrics. You can use the update autoscaling command to add schedules to existing autoscalers. The set schedule parameter creates a new schedule with the name you provide. This name identifies the schedule for future updates or deletion. Use descriptive names, for example, business hours, weekend reduced, or Black Friday sale. The schedule cron parameter uses standard cron syntax with 5 fields: minute, from 0 to 59, hour, from 0 to 23, day of month, from 1 to 31, month, from 1 to 12, and day of week, from 0 to 7, where both 0 and 7 are Sunday. Use an asterisk for any value, ranges like 1 to 5 for Monday through Friday, and lists of specific values like 0, 15, 30, and 45. Common patterns include 08 asterisk asterisk 1 to 5 for 8 a.m. weekdays, 0/4 asterisk 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 for every 4 hours, and 021 asterisk asterisk for 2 a.m. on the first of each month. The autoscaler evaluates these in the time zone specified by the schedule time zone parameter. The schedule time zone parameter accepts TZ database names like America/New York or Europe/London. Never use abbreviations like EST or GMT as they do not handle daylight saving time correctly. The schedule automatically adjusts for DST changes in the specified time zone. The schedule duration sec parameter defines how long the schedule remains active. After this duration, the schedule's minimum number of instances no longer applies. This prevents forgetting to scale down. Your business hours schedule automatically ends without manual intervention. The schedule min required replicas parameter sets the minimum instances during this schedule. This overrides the base minimum but not the maximum. Regular metric-based scaling can still add instances above this value if needed. The schedule description parameter adds human-readable context. Use this to document why the schedule exists. For example, scale up for East Coast business hours or prepare for weekly batch processing. Advanced mode and update parameters. Several advanced parameters control the overall behavior of your autoscaler and how it makes decisions. The mode parameter has 3 values. On enables normal bidirectional scaling. Only scale out or the older only up allows adding instances but prevents removal. And off disables the autoscaler while preserving configuration. Use only scale out during critical events when you want to handle increased load but avoid any risk of reduced capacity. The CPU utilization predictive method parameter enables machine learning-based predictive scaling. Set it to none, which is the default, for reactive scaling only. Use optimize availability for aggressive predictive scaling that favors availability over cost, or standard for balanced predictive scaling. Predictive scaling works best for applications with regular daily or weekly patterns. The clear scale in control flag removes scale down controls, reverting to unlimited scale down. Use this with caution, as it can cause rapid instance removal. Similarly, the remove schedule parameter deletes a specific schedule by name, and clear schedules removes all schedules. When using update autoscaling, you're modifying specific aspects of an existing autoscaler. You can update just the cooldown period, add a schedule, or change the target CPU without affecting other settings. This is less disruptive than set autoscaling, which replaces the entire configuration. The project parameter specifies which GCP project contains the MIG. This is usually unnecessary if you've set a default project, but it's essential when managing resources across multiple projects. Similarly, the verbosity parameter controls the output detail, which is useful for debugging or scripting. Remember that some parameters are mutually exclusive. You can't use CPU scaling and load balancing scaling together. Schedules complement metric-based scaling but don't replace it. Understanding these interactions helps you build effective autoscaling configurations. Thank you for your attendance. Please consider subscribing to the channel.